All right, so I guess it's time to get started. Hi, everyone. Welcome to my session today. I'm super excited to be here in Copenhagen. This is my first NDC event and my second time in Copenhagen. Yeah, welcome to my session. My name is Alina Dima. I'm a developer advocate. I work with IoT, and I have been with Amazon Web Services for about 4 years, starting in professional services, where I was working with customers on helping them build IoT solutions that scale with AWS, of course, and serverless technologies. And then I moved to a developer advocate role, which is more about working with the community, which I really enjoy, and helping developers out there build better and faster with IoT. The session today is going to be about mixing IoT serverless towards building IoT workflows, and of course, leveraging the power of the cloud. And I'm going to throw into the mix a mathematical concept of state machines as well, which is going to facilitate breaking down complexity. So let's get started. First of all, how many of you have worked with IoT? Okay, that's quite good. What about AWS IoT? Okay, very good. Yeah, so for those of you who are working actively in IoT, you probably know the context. IoT is really about an ecosystem. So when you're working on in IoT, you're not really working on one side or a really narrow domain, but you're working in the IoT ecosystem. So devices out there are increasing in numbers. So we're going to be reaching billions at one point. And of course, with the increase in the number of devices, we need and have needed for quite a while to introduce remote device management. Of course, there are a lot of standard bodies and there is a lot of standardization in process or in course, and a variety of standards. So you can literally find different protocols for different industry verticals, for different type of devices with different kinds of constraints. When you are actually trying to manage a fleet of devices, you are trying to focus on heterogeneous device fleet. So you try to manage with one management system as much as possible various models of devices of various generations, next generation powerful devices, sensors, actuators, gateways, and so on, ideally as much as possible with one device management solution. So remote management is crucial because you can't go with a USB stick to your devices and try to update them over the air, for example. And configuration settings, of course, also needs to be done remotely. So all these things are increasing expectations from device management systems. Also, not to mention security, which security and safety has become more and more of a concern over the years. I mean, consumer electronics, for example, you want the devices in your home network to be secure. You want the devices in the factories to be secure. So this brings me to the point that in order to perform remote operations on devices, you are really talking about distributed systems. So it's never about just what executes on one device. It is about a mix of operations that need to be performed together as part of a workflow. I mean, imagine firmware upgrades. We're going to talk later on about that. And I'm going to also give you some other examples. But it's never about just what one device does. It is about what millions of devices could potentially do and their interactions with other systems when it comes to remote management. And of course, devices have different constraints. Integrity is key. What you don't want to have is out of your fleet of 5 million devices, for example, 10% being totally bricked and you not being able to communicate with those devices. What happens if devices reboot in the middle of a software upgrade? What happens if they have intermittent connectivity? What happens if one operation of an entire workflow gets executed, but the rest cannot because your device is no longer available? What about power cuts? What about battery losses? So we are going to be talking about workflows in this session and processes that are executed on devices. In terms of the goals of this session, I want you as a takeaway from the session to understand what IoT processes are, what are the challenges and expectations. We're going to look at 3 different ways that you can design and build an IoT workflow solution. And of course, we're going to talk about orchestration from the cloud, and we're going to talk about state machines. And eventually, I want to do a live demo of a solution that I've built using one of the design approaches, which I consider the most appropriate to solve the problem. So we will have a live demo at the end as well. One thing before we start is to understand that when you're building workflows in your architectures, it's not about one device management protocol. For example, you want to maybe support the Meta standard, or you want to support LWM2M as a device management center, or you're dealing with modem routers and you want to support one of the broadband forums, DR369 protocols. That matters, of course, but that's not the whole point of building a workflow. So you need to build abstractions so that if at one point of time you need to support new devices with different protocols, you don't have to rebuild and modify your entire architecture. So this is what it's all about, abstracting and building resilience in that. So let's see what are device workflows. So throughout the life cycle of an IoT device, generally you encounter different processes at different stages in the life cycle, right? So the first stage is deployment. This is when the device gets prepared to be sent out there in the field. So here you have provisioning of the device. This can mean different things based on what industry you're using your IoT device in. So one thing is for sure quite common in all industries, and that's about security, right? It's about provisioning credentials onto your device. If you're using mutual TLS, for example, you need to provision a certificate that is unique per device. You need to provision a private key, which is also unique per device. This generally gets done in the provisioning or onboarding of your device. If you have consumer electronics, then you might want to facilitate the journey of your users by enabling settings out of the box on their devices. Here I'm talking about users potentially having an online profile and you as a device manufacturer pushing that profile onto their devices. So when they plug their device in, they can simply get their configuration settings. So this is also a workflow, right? When the device is in operation, you need to be able to update the device over the air. You need to be able to implement use cases like data collection, right? So you might be interested in doing remote maintenance in a factory. You want to be able to collect the data in an easy way to read insights into that data. So here is another workflow. The maintenance is really important. Security updates, bug fixes, over-the-air updates, certificate rotation. And actually, as a comment, the certificate rotation can be a long-running workflow that resides somewhere and that is dormant until the moment in time comes when your device needs to be, when the certificate on your device needs to be rotated. So all these different workflows, and I'm not forgetting decommissioning, when, of course, you want all the sensitive user data to be removed once the device has reached the end of life. All these workflows have common characteristics. I can call them complex or I can call them sophisticated, whatever you prefer, but there is actually a certain level of complexity and interaction with different proprietary systems, cloud systems, security, authentication, data stores, and so on, that need to be performed. Also, the execution is distributed and you want to have remote triggers enabled. Some of the workflows can have the need for a human to approve the workflow before the device is prepared to be remotely managed. And of course, you can have long-running workflows as well, like I mentioned. So the whole point is to simplify this. So what is the mechanism to simplify the workflow complexity and split it into simple tasks? This is an example of a workflow which is about fault troubleshooting, right? So you can see the steps yourself, but so I am an operations, I lead an operations team, for example, and my operations team would like to actually get insights and deeply inspect what is going wrong on a set of devices. So you'd imagine that you enable this deep inspection for, let's say, 30 days. You gather the insights from your devices, you understand the problem, you troubleshoot it, you prepare a patch, you actually OTA the patch to your devices, and then you want to disable this deep inspection. And here's a workflow to actually do this. In terms of challenges when it comes to workflows, I think here the challenges can be really grouped in 4 different categories. So you've got reliability challenges, right? So what about workflows that need to talk to external systems? What are the SLAs? How many retries do you have to do? If you need to do retries from embedded devices, that's probably not even possible and not even realistic, right? What is the backup strategy? So this kind of challenges. Visibility and observability is also important. how do you actually put in place metrics that you can gather so you understand what is the percentage of your fleet that has been successfully updated following the workflow? How many of the devices have failed, and what is the most common failure that you encounter? These metrics, of course, it's good to have them at device level, but it's even more useful to have them at fleet level. So when you decide where your workflow needs to be distributed and how, you need to imagine that you might want to put in place an observability solution that looks at executions of the workflow, not just on one device, but also as aggregate on a fleet of devices, independently of what kind of devices they are. Flexibility and expressiveness is also extremely important. So a new business requirement comes in that involves you needing to modify a workflow, right? So for example, there's a change in the system that manages customer data, and you need to make an extra step in your workflow or introduce an extra step in your workflow to retrieve the new, I don't know, account IDs, for example. How difficult is it going to be to actually build this step? And when we go through the different architectures, we're going to talk about how difficult or how easy it actually is to extend your workflow. What about new devices, new device management protocols? How easy is it to integrate these protocols into your workflow management solution? And of course, navigating complexity. So we are dealing with IoT devices, and it is a little bit different than back-end systems that run on servers, right? Devices are in the field. There are hardware constraints. There are networking constraints, protocol constraints, a lot of third parties, and a lot of teams are in the mix, right? So there is the edge team that builds, firmware or application firmware. Sometimes you even have firmware vendors. Sometimes you have OEMs and other partners. Drivers are being built as well for your devices. So there's a lot in the mix, and this is just the complexity of IoT. But also, you are dealing with distributed systems. So all the problems about who is orchestrating, who or what is orchestrating your workflow, how do you roll back? I mean, if something goes wrong, you might want to roll back your workflow as a unit, not just a particular task or operation in your workflow. So all these are challenges that you need to solve when you're building an IoT solution that involves workflows. If you are to actually put the expectations that you have from such a system together, you could build a maturity model that simplistically looks a little bit like this, right? So you have some basic set of requirements. And this is generally what protocols or standardization helps you with. This is what happens at operation level, right? So basically, you need to have APIs or interfaces to your device that help you do primitive operations. So set parameters, on your device, read parameters from your device, send operations to your device, and so on and so forth. So that's one thing. You can assume that that's mostly there. Sometimes when it's not, then you have to build it in. The communication protocols are defined, and there is a specification that you're using, right? So you know the requests and responses. If it is synchronous or asynchronous or event-driven or non-event-driven, it doesn't really matter, but something is specified. And of course, integrity and eventual consistency in your atomic operations is important. You want, ideally, that the primitive operations can be rolled back if you need to roll them back. Aggregations are about encapsulations of primitive operations, but also the ability of a system to mix different operations together to build a workflow. For example, when you're talking about a firmware upgrade workflow, you send a command to your device to update, to download the new firmware image. You might want to actually have either a different operation that you call afterwards to activate the firmware image, or you might mix them together, download and then activate, if it's possible to activate the new firmware image. And of course, this is just the operations that happen on your device, but understanding if the desired firmware version is valid, understanding if the user is authorized to perform, or the operator is authorized to perform this firmware upgrade, that's another operation that you might want to throw into the mix in your workflow. About flexibility, we already talked, right? So it's important to be able to configure in your system everything from inputs and outputs and retries of the workflow as a whole, or retries of each operation individually, based on the kind of design that you will put in place. Of course, your solution needs to scale. I mean, generally, I think IoT nowadays, we've kind of overcome the challenges of building a prototype to a certain extent. So it is mature technology. We are no longer in the early days of IoT. But what is still quite complex is performing functionality at scale. So building scale and ensuring resilience and ensuring operational excellence, it's something where we still need to work. And this kind of work needs to be done in all industries, right? So when you're building a workflow, you need to imagine how the workflow can scale to more operations inside the same workflow, but also to more devices, right? When you're talking about intelligence, here it's about device targeting, right? So could you build a workflow that automatically targets a group of devices based on some device properties? The device properties can be static, for example, upgrade all devices that are on firmware version 1.1.1, we will see this later on, or upgrade all devices that have Wi-Fi setting X set to Y. You know, these kind of things. They can be dynamic or they can be static. Concurrent run, right? So if you have a group of devices, you might want to run multiple workflows at the same time concurrently on your device. Sometimes it's, of course, no problem. If your device is extremely powerful, then you know, an edge gateway might have no problem to run this. But what about an embedded device that literally has a real-time operating system on? Right, so now let's talk about design approaches for the workflows, right? So what different design patterns could you adopt to actually build such complex workflows? Here we're going to try to differentiate in two ways. So it is about who owns and drives the workflow. Is it the device owning the workflow and driving the workflow? Is it the cloud driving the workflow? And then in addition to where the workflow runs and who owns it, it's also about the nature of the execution and of the workflow manifestation. So do you know that you have a workflow? I mean, very often, and I've worked in distributed systems, I sometimes jumped on projects where a lot of the solution was already in place. And there was a workflow there behind the scenes, hidden in between 50 systems, but the workflow was not explicit. So it's about how the workflow manifests. Is it in the head of an architect and lead engineer, or is it readable in your code? So that's the other criteria. So we can look at device-driven workflows. We can look at embedded cloud-managed workflows. And by embedded here, I mean implicit manifestation. So this is what I was talking about earlier, 50 different systems running part of the workflow, responsible for retrying and so on, but there is no workflow to the outside world, not explicitly anyway. And then we're going to talk about externalized, cloud-managed workflows. And this is the part that I will go into details about. Because, and I will show you, this is scalable quite nicely, and it fits into our resilience principles as well. So let's see how a workflow would look like if a device is actually driving the workflow. So, of course, here, the device is responsible for defining what the tasks in the workflow are, is also responsible for initiating and driving the execution of the tasks, and the device would also be responsible for managing the state of the execution. So this is how it would look like, right? So you still can have this thin device management layer which ensures that remote triggers are enabled. And you still can have some job scheduling and processing component that literally pushes job executions into a queue and then signals the device management component to trigger the execution of the workflow. But the bulk of the work will be done here on the device. So let's see what's good about this, right? So for devices which are not really constrained, this can work actually quite well, right? If you've got an efficient over-the-air mechanism in place on your device, you can actually do this. If you have use cases where a lot of the interaction for the workflow is happening inside the network where your gateway is located, for example, imagine that I'm trying to set up some network profiles based on what people are doing in their homes, right? So if I want to watch lots of Netflix, then I'm expecting my telecommunication provider to actually ensure that the profile set on my router enables me to do this. So if it's this kind of use case, it actually might work. It also works for devices that, due to security reasons or bandwidth constraints, cannot communicate to the internet that well. And also in cases where the workflow changes actually not frequently, this can work quite well. But of course, this cannot work on constrained devices. You can't do this on an embedded device. This also leads to fat edge applications. And I mean, if you are all good with having a fat edge application, then it's no problem. But if your OTA mechanism is not quite there yet, and you do a firmware upgrade once a year. Let's hope this is not the case anymore nowadays. But imagine you have that kind of scenario, then that's not going to work. If new requirements come in, you need to do either a configuration update to your devices to introduce a new step into the workflow, or you need to really do a firmware upgrade based on how your implementation is. Of course, from a resilience perspective, it's the communication with external systems. I mean, I've named them A and B here. This is done from the device. So the device needs to manage retries and exponential backoffs and so on. So not ideal, but based on the use case, of course, you can do it. The other way is different systems managing different parts of the workflows, the workflow actually being implicit inside the code. We talked about this. You've got different services. They can be located in the cloud. They can be running on-prem. It doesn't really matter. And the device management system is actually just doing the talking to the devices, but all the other systems are performing their own tasks, right? And it's a workflow internally, but it's not visible. Of course, this is easy to implement, and based on the complexity of the workflow, might work well. For small IoT fleets, it's no problem. When you need to scale, the tight coupling might make it a problem. And when you need to introduce new workflows or new steps in the workflow, it's really quite disruptive to the whole system. It's also quite disruptive to engineering teams who need to just modify something that theoretically could look quite small. Regression is quite likely, so you need to do a lot of testing. And of course, there is no centralized end-to-end status tracking. So when you would need to build a monitoring solution in place, you need to ensure that all the systems are reporting properly. And you can do it, but it's quite a bit more work. So now let's look at an externalized system. So here you really have one component, and I've called it here external workflow management and execution. This component is responsible for defining the workflow and for orchestrating the execution of the workflow. And also for managing the state, right? So not the state of every task only, but also the state at workflow level. And workflows can be executed as a unit. If you need to roll back the workflow as a unit, you also can do so. And this component is going to enable you to trigger the rollback. Of course, you still need to make sure that your operations are built idempotently and also that you can roll back. But doing a rollback with this kind of architecture, it's just the engineering saga pattern implementation, and you can actually do it. Of course, you need to make sure that your device can also roll back, which is another aspect that you cannot run away from. But yeah, aggregating the state and building a monitoring system, that can be done on top. Some services actually can help you quite nicely with that. But if you're building this yourself, of course, you need to build the monitoring system. Of course, this works quite nicely for scale, but it makes the assumption that you are building this in the cloud. If you're not building this in the cloud, then you're going to have quite a bit of work setting up the infrastructure needed for this kind of architecture. But when you're dealing with millions or 10 millions, 1 million, 5 million with scale, then you need to build for scale. And this is what this architecture resides. So now if you look at this architecture, you already probably can imagine where the state machine comes in, right? So it's modeling this part, the actual workflow, with a state machine. So let's see why we actually do this. So this is the definition from Wikipedia, what state machines are. I think most of you are familiar with state machines. It's about breaking complexity, creating a finite number of states, and ensuring that the transition between the states is specified and that the behavior of your workflow is deterministic at every point of time. So transitions would happen based on events, or they can happen based on inputs, based on state history, based on outputs, and so on. Scientifically, I mean, state machines have been used for quite a while. They've been used in hardware design and hardware implementation. They've been used in software implementation, in software systems. So it's actually not a new method. Let's see how we can actually apply it, and first of all, why. Why shall we do it this way? We don't have to do it this way. This is just a proposal. It just makes it elegant, right? If you know from one state all the states that you can actually go to, and if your transitions are defined, if your actions are defined, that makes modeling of complex behavior quite easy and quite straightforward. It can also help with a loosened temporal coupling, right? So if you have a lot of workload that you need to execute. And part of this work depends on other systems. What you want is to execute small pieces of logic, small units of logic that can be executed faster, as soon as they can be executed, instead of waiting for the results from another system. You can, do things, and you will see later in the demo how that can be done. Okay. So generically, this is how this would look like, right? So you've got here your orchestrator component. Users or developers can define the workflow the way they want. Can do it via code, depending of course, what services you're using for the orchestrator. And then you split the functionality of each workflow into a state machine. And actually, you see here that the workflow itself is defined here, right? So here you have the state machine definition. And these are the executions of the state machine on various devices involving different systems, so on and so forth, right? So it's all just an evolution from the externalized workflow management that we talked about earlier. So now let's take an example, because we've spoken quite generically and theoretically so far. So let's talk about firmware upgrades, mostly on embedded devices. So what are the factors that influence firmware upgrades on embedded devices? So it's about memory constraints, it's about hardware costs, it's about the entire ecosystem that gets involved in a firmware upgrade. So I will show you in the next slides how to build this with a state machine. But just a few assumptions that this is making. So generally, when you're doing firmware upgrades on embedded devices, A/B partitioning is quite a known and quite an established mechanism. So this means that your device is running a particular firmware image on one partition, which is the active partition on the device. And when you're doing a firmware upgrade to a new image, the new image is going to be downloaded in a non-active partition on your device, right? So this basically means that at one point you will have one firmware image active and another one pending. When your device boots, or when you instruct your device to boot, it's going to attempt to boot in the new partition, and if it can do so, then it's going to keep the new partition and the firmware upgrade would be successful. And if it can't, then it's going to nicely roll back to the existing partition. So this is the process that we are going to be describing in the next slides. Of course, the process of creating images and versioning and so on, that still needs to be in place, but that's a separate topic. From a simplistic operator view, I mean, we want the operators to have fun as much as possible with the system, so we don't want it to be too complex. So the operators would try to understand what the current firmware version on the device is, and would try to download and activate a new image, and then verify the success, right? So check if the new image has been successfully downloaded and installed and activated on the device. Of course, like I mentioned, you can do two operations. You can first download, verify the download, and then activate and verify the activation. From a system perspective, it's also not very complicated, right? So the system would get a firmware upgrade request in. It would validate the information for the firmware upgrade, right? So does this image exist? Is the user allowed to actually perform the firmware update operation, so validating permissions, and then it's going to send the operation to download and activate to the device, process the device response, and understand success or failure. So this is the workflow from a simplistic view. As a state machine, you can actually build the same steps that I was talking about before and fit them into our overall big picture architecture. So you've got the start of your state machine, you've got validating the device, right? So when you're trying to perform a firmware upgrade, a system needs to check if the device exists, if the device is online, and all kinds of other things, right? Permissions need to be validated, firmware metadata validation needs to be performed, and only then you can go on at sending the firmware upgrade operation. And then, based on the device management protocol, and here, this is where your workflow is a little dependent on not the low-level details of your device management protocol, but the overall workflow, right? So, is a download operation what you need to send to your device? Does your device send you an event when the operation has been successful? So assuming that this is the case and your device supports this sort of event-driven interactions, then you can build something, you can build some wait states waiting for the device to actually respond to the different operations, like the transfer of the new firmware has completed, or the download operation is done, or the device has booted into the correct firmware image. You can interpret these events and then know about success or failure. Right. So I will leave this maybe for like 10 seconds to sink in, because the next step is to talk about how to implement that. And of course, the implementation I'm going to show you is at POC level, perhaps, if you can call it like this, or maybe MVP level. It's you know, something basic to get you to understand the concept. So let's see how we're going to do this, right? So in terms of implementation details, I've just mapped this to AWS services so that it gives you a picture of what component is built how, right? So you've got the job processing and scheduling. This is a good match for AWS IoT device management. So this is built with, the orchestration of the jobs is built with IoT jobs. And the grouping of devices and targeting of devices that I will show you later is going to be built with device management. So IoT device management, grouping, dynamic groups, and static groups. Of course, behind the scenes, the core of the connected solution, the backbone in my demonstration is going to be IoT Core. So you will see IoT Core, devices connected to IoT Core, and the rules engine to route messages that go from the cloud to the device and from the device into the cloud. The workflow management and execution, and this is quite interesting, I've opted for step functions to actually support with the workflow management and execution. And this is because the entire architecture that I'm building in this proof of concept is serverless. So I'm going for serverless technology so that the operation overhead is quite small. Of course, this depends on use case and on preferred mechanisms if you want to build this non-serverlessly. In terms of device management, this is just IoT Core and IoT device management. And the devices, I've created an application, an agent, how I call it, that actually responds to the cloud, to the messages from the cloud. Behind the scenes, the implementation on the device. So this agent is simulating modern routers and modern router protocols. And it's basically simulating this protocol called TR369. This is to make it resemble a real-world use case. However, the device management, the device management protocol itself can be replaced easily with something else, and only a component in the system would change. It's a Node.js runtime, and the agent will be running in Docker containers. I'm going to show you in the demo initially one Docker container, so we can look at one state machine, and we can see the execution on one device with the systems that it's actually interacting. And then I'm going to start probably like 100 containers and show how this actually looks like on 100 devices. Or I don't know, 150, whatever. In terms of infrastructure, I've used SAM because it's easy. And it's also, to build a proof of concept, I don't know, you can use SAM, you can use Amplify, you can use CDK if you want, or, if you're not building this on AWS, I have a slide at the end to show you the open source technologies that you can build this with. Okay, one last thing before I show you how the architecture looks like, and that's in terms of design considerations. And I think this is important, right? Because if you look at all the different components, one thing that I have done is focus on some architectural principles to make my implementation easy, right? So I want to have bounded context. So I want each component to have clear responsibilities and be responsible for the domain and for the domain logic within that component. Components are loosely coupled, so if I decide one day that I want to change the workflow management and execution, I don't have to modify anything that is outside the boundaries of that particular component. The communication between components is done via events. So you're not going to see one component making direct API or SDK calls to, for example, the workflow management and execution. It's all going to be event-driven using SNS. So I'm going to use SNS for the demonstration purposes. The domains are encapsulating of course, the logic in the domain, but also retries, error handling, and all the responsibilities of that particular domain. So ensuring eventually that there is success within that domain, if possible, of course. This is the architecture on a high level. I'm going to walk you really quickly through this. So a firmware upgrade request comes in. We're going to simulate this by triggering a Lambda function ourselves, saying, hey, upgrade the firmware on this group of devices. Of course, you can build an API on top of this quite easily. Then behind the scenes, we're going to be targeting an AWS IoT thing group. There's going to be a message published, which is going to start the workflow, right? And here the workflow will involve a bunch of tasks that will be executed, which will involve, to a certain extent, message exchanges between the workflow management and the device management component, right? So you're going to be like, start download. This is going to be a message that's going to be published by the workflow management onto an SNS topic. And the device management component is going to pick up this message from the SNS topic and is going to be responsible for communicating with the device and telling the device what to do, right? So the communication between the device in our architecture, it's all over MQTT. So it's done because of the relationship with modem routers and the fact that the device is respecting the TR-369 protocol, the messages are protobuf encoded in this architecture. So here is going to be protobuf over MQTT, but the levels that are above here are not going to know anything about protobuf, right? So that's going to be device management and device understand protobuf and protobuf specification. The cloud actually is not responsible for, the cloud components that are above are not responsible for knowing anything about that. When the device is ready with the events for the asynchronous operations, it's going to publish messages on the reply to topics again, and this Lambda function here is going to publish the SNS messages that the workflow is listening to, right? At the same time, the workflow, when certain groups of operations are done, is going to inform the job processing that the job executions have been successful, right? So what we want to make sure is that eventually there is an answer to the firmware upgrade request. That there is a response. Of course, it's all going to happen asynchronously. Initially, requests are going to be accepted, but eventually there will be a status update, and we're going to cleanly terminate the job executions in this job processing component. I can take any questions later about this architecture, but for now, for the purpose of time, I'm gonna move on, and yeah, I think the next step is really for me to show you this. This is not very visible, so we're going to go into the console and look at the state machine. Yeah, so without further ado, let's do a demo. And this is going to be live right now. So I just want to say I set up an EC2 instance because I do want to run a lot of containers, and I don't want to do it from my Mac. So I've set up an EC2 instance. I've cloned the code. By the way, the code is open source. You can have a look later. There will be a slide which is going to give you access to this code so you can run it yourself. So I've cloned this code on the EC2 instance, and we can see that we have here the workflow management and execution. So what I'm going to do first is I'm going to start one agent, so one device. Let's see how we do this. So first of all, the architecture here, you can also see. So all these domains that I was talking about, they are separated in code packages as well, right? So you'll know what is responsible for job processing, what the component for the agent simulator is, what device management component is, and what the workflow implementation, where the workflow implementation is all located in. So let's go to the device agent simulator. And in here, I've created myself a run script. I mean, I'm not very proud of it, but I will show you anyways. So this is just a little bash script that basically loops through a number of devices that I want to start, and just literally starts this simulator application as many times as I specify. So it's nothing so complex. So far, I've set it to 1. So let's start one simulator here. I think we will start it with bash because it's easier. So this just builds the Docker container and has already started one instance. If we look in the logs, I'm getting there. Let's see, so this has started, it has created this IoT thing on the AWS cloud, it has created the key and certificate, attached the thing principal, so this is part of the onboarding process to AWS IoT. and it literally subscribed and prepared my agent to receive communication from the cloud and also respond to and also send, its own events to the cloud. So if we look on the cloud side, let's see what happened there. So if we go to IoT Core, we should probably see that there is one device. Yeah, we've got one device. This is our IoT device that we created. In preparation, I have created 2 thing groups. So this is for dynamically grouping devices based on their current firmware version. So these are dynamic groups, and they are grouping, for example, this is grouping devices that are on firmware version 1.2.3. And the other one is on the default firmware image. So our device, because it just booted up, it's going to be on the default firmware version. So we see it here. So right now, like I said previously, I don't have the slide anymore, but like I said previously, we're going to trigger the entire firmware upgrade workflow by executing the lambda function, right? We can execute it against this group, which only has one device. We could also do it on the device independently. So let's see. This is the lambda function that I was talking about. I mean, we can go through the code really quickly. It's a very simple, actually we can't go through the code here, but we can go through the code here. It's a very simple create job AWS lambda function. I mean, the entry point is the lambda handler, and I hope you can see this is just creating an IoT job from an event that comes in, right? So it's parsing from the job document the firmware version. It's getting a trigger. The trigger is set to manual because I'm manually triggering the execution. You could imagine a workflow where firmware upgrades are executed automatically or triggered automatically. For example, you might have a use case where I plug my device in my home, and an operator wants that the device automatically goes to firmware version x.y.z, and then you trigger this workflow as an automatic workflow. Right, so this just creates the job. So it's a very simple lambda function, and to test it, we just give it a payload. So I want my device to go to firmware version 1.2.3. My trigger is manual, and the target, like I said, we are targeting the group, the thing group, but we can target the device as well. The thing group has one thing, so there is no impact. So I'm just going to trigger the test of this. And if you have a look, I mean, this has been very fast because the only thing that happened is that a job has been created. So behind the scenes, the workflow is going to get triggered. Now, to look at the workflow, we probably should go to the state machine. This is the firmware upgrade state machine. So again, if you look here in the AWS IoT console under state machines, this is the definition of the state machine, right? So and I will show you later, you can go and see the definition of the state machine in more detail, but here you see the executions, right? So there is one execution running, which is what we expect, because we've triggered this on one device. I mean, it's already been successful. I don't know why this looks actually so weird here. Let's see, can we make it smaller? Can we make it even smaller? Okay. Let me see. Yeah. Okay, so this is probably now big enough for everybody to see. So this is, it's been successful in our case. So this is the state machine execution. So it shows you, I mean, all these green states basically mean that the transitioning has been successful through all these states. So the first thing that I will show you after the actual definition, so you see what services have been executed and what service calls have been made behind the scenes. But in terms of the state machine itself, it's like, give me the device. Does a thing with this, in this thing group, with this thing name exist? Is the thing connected to MQTT, right? So if I actually shut down my Docker container or I remove connectivity from my Docker container, the state machine is going to stop here, right? At here, device not connected. So we're not going to execute anything longer because it doesn't make any sense. My device is not connected. So if all these things are actually successful here, which are the pre-checks, then the next step is to trigger the download. And here, this is the step that sends an operation to the device, right? So this is the step where device management, that component we were talking about earlier, is going to publish an MQTT message over IoT Core to a topic, to an MQTT topic that the device is listening to. So it's all about this, this start download. In the meantime, this start download is going to wait a little bit to get an acknowledgement. The acknowledgement is actually synchronous, right? So it's not going to be, it's not an asynchronous operation. So start download, if the operation is accepted, get an acknowledgement and move on to these waiting states. And now here, we're going to be waiting for 3 different events that our agent is going to publish as it progresses with the firmware upgrade. So we're waiting for a transfer event, download operation response, and reboot it. If all of these are actually happening, of course, when the boot message is received, we should update the thing attributes with a new version, so we actually know that the device has updated successfully on a new version. Then the firmware upgrade is complete, is successful. The firmware update completed state is successful, and we can publish messages over SNS to inform the consumers of these messages, meaning the job execution and processing component, that the workflow has successfully completed. So this is how the state machine execution looks like. Now, the nice thing about this is that, remember we were talking about flexibility and we were talking about expressiveness. You can see the input and the output into each of these states, right? So you clearly see what is the input into the state, what has caused the transition, and what is the output when the state execution completes. I mean, of course, this is how this looks like with step functions, but with other services, it's probably going to be implemented differently. But ideally, you should look for a service that actually allows you to do this granular input and output configuration. You also can see here all the states and the transitions and how everything executed on one device. If we go back to the logs here, you see the messages that have been sent to the device and how the device is sending the boot event. This is all protobuf, like I said. It's perhaps not that interesting, but something has happened. The device has interacted with the device management cloud side, and messages have been exchanged. And I'm not being crazy saying that a state machine executed. Now, what I do want to show, before we move on, and I think I still have a bit of time, I want to show you the workflow itself, right? And I'm going to try to make this. This is the workflow definition, by the way. So again, workflow definition, one thing, happens one time. Workflow, I mean, not one time, but as many times as you want to define a workflow. So once per use case or per workflow. Executions happen many times as you have devices. So if I try to zoom in here, let's see if this works. Yeah, it kind of works. Let's make this smaller. Okay, how is this now? I think you can actually see. Of course, now I did want the inspector a little bit. Again, here it shows you the definition and what AWS services or non-AWS services are being invoked behind the scenes. Yeah. So, sorry about this. So again, this is a call to get device. This is happening via the indexing service of AWS. So this is to ensure that the device actually exists. Does the device exist? Is the device connected? The same information is going to come from the indexing service. The next steps here are mostly parallel states or pass states or choice states, which literally just parse the output of this state here, right? So it's just some logic to actually understand, can we do the upgrade or can we not do the upgrade? Again, here, we are starting the download operation, and behind the scenes, we go into this parallel state that waits for device messages. These DynamoDB operations are actually also quite interesting. The reason why we need to store state when we are dealing with asynchronous communication is because we do care for the asynchronous response from the device. So we told it to start download, but has it actually downloaded? For that, we actually need to store a token and wait for a callback. The callback is going to be invoked when the message comes back from the device. So we do have a little bit of state management here, and this is the reason why we have a bunch of DynamoDB integrations for each type of message. Update thing is quite clear. This is an API call to the AWS IoT thing. What's interesting here is that there is no code, right? Of course, there could be code if you need complex logic to run a Lambda function, but if you need to simply integrate with an AWS service, you can do it behind the scenes by using the native integration of step functions. Right. Publishing is again happening over SNS. So yeah, you can have a look at this in detail. If you deploy this to your AWS account, you can definitely have a look at this in detail. So the next thing, and I think maybe what's happening is that I need to re-authenticate because I might have lost. Okay. Reload the page. Yeah, this happens every now and then. So the next thing that I want to show is, let's try and do this now on 100 devices, right? So what I'm going to do is I'm going to change this run script. I'm just going to go quite brute force, but yeah. So remember, we still have this device. I'm not going to stop this device. It's still running. Let's let it run. But now we're just basically going to start 100 containers, create 100 containers. So let's do it. It's going to take a little bit, but it's going to eventually get there. And hopefully in my AWS account, I can show you how new devices are being created. Yeah, we're expecting to have in total 101 things because there was one from before and another 100 that I'm creating. So it's going to slowly get there. Yeah, so all these things are actually looking the same. So they don't have different properties. I mean, I'm really like simulating on a basic level, creating IoT things with a certain software version, like 100 devices that look exactly the same on the same software version, sending a first boot event, and that's basically it. Yeah, and let's prepare. Let's see how the thing group looks like. So theoretically now, because we updated one device, we have one thing on the new software version, the new firmware version 1.2.3. So that's fine. The other things, the 100 of them, are going to be on the default firmware version. Yeah. So let's wait a little bit and before we trigger the firmware upgrade. Or maybe I can just trigger it on the things that are available. I mean, the important thing really is that it's going to be 100 of them eventually. So let's do the same thing again. This means that we're going to lambda function, trigger the lambda. So here you'll see all the lambda functions that are part of this solution. The one we actually care about is the create jobs. We go to test. We run the test. Here it is, the execution has been done again. And if we go to the step functions again, we should see, I don't know, based on how many devices have managed to start, how many containers have managed to start, we will see a few of them. So probably the ones that have failed are for devices that have been created, are part of that group, but are not yet MQTT connected. So yeah, this is bound to happen. As well, which is fine. So we will see some failures. And now let's see, there are some still running. If we look at all of them, yeah, some have succeeded, some have failed. Now, the interesting thing, let's see where this failed. It's probably, yeah, the device has not been found. So this means that the entire MQTT game for some of the devices was not ready because I didn't want to wait for the entire time. So I mean, this. Let's see, how many have we managed to do? Okay, so we have about 77 executions. The other devices are still, getting ready. The nice thing about this is that you have visibility into each execution. You also have visibility into what step went wrong at what point, and so on. And of course, you can use logging services like CloudWatch Insights to get aggregation results on your entire fleet. Right, so I think this is all for the demo. We can definitely talk about it more in detail. Before I open up for questions, I know I'm running a little bit out of time. I do want to say that if you want to build this with open source technology, yeah, there are some open source tools that also can help you build something very similar. Temporal is actually a really good workflow management and execution open source library or software. Observability can be built with other tools like Datadog, Grafana, Prometheus. You can extend the device agent to actually support protocols like Matter or LWM2M or any other device management protocol you wish. And of course, I would love to explore in the next iteration workflows such as some smart home automation, like for example, I come home and my coffee machine is making my coffee. In the meantime, I don't know, my microwave is preparing me something, you know, some kind of workflows that are a little bit more out of the box than what I've shown you today. And robotics, of course, is another thing. Resources, the GitHub repository, you can find if you scan this QR code. You can also look at that URL. There is a blog post that I wrote about this. And also there is one blog from Werner Vogels, which I really, really like, about distributed computing, where he really proposes a distributed computing manifesto, which is quite interesting. It does not refer to IoT, but a lot of the principles, of course, apply to IoT solutions as well. So this has been all for my session today. Thank you very much for your attention, and now I'm going to open it up for questions. Any questions? Oh. Thank you. Okay. No questions. Wow. This means everything was clear. Yeah, I see. Anyway, if something else comes up, I am around today. I'll be around tomorrow as well. So reach out to me on LinkedIn if you want. You can scan that QR code and we can connect. Thank you.